Hello, everyone. My name is Roy, and I am a PhD student from the University of Sheffield. It is my pleasure today to introduce our work based on the ICEP COVID Grant Challenge. And our team developed a deep learning framework for the COVID-19 detection using CT scan images. There are two participants in our team, me and my supervisor, Dr. Charis, and I will be the one to present the work here. To begin with, let me show you the outline of today's presentation. So this presentation is divided into three sections. First, I would like to talk about the background information of the competition. Then I will elaborate our approach and how we implemented it. Finally, we will land on the result and discussion. So let's get into it. Recently, there has been a number of studies demonstrating that deep learning-based applications is helpful for physicians and radiologists to make more precise diagnosis. Therefore, considering the continuous impact of the COVID-19 global pandemic, it is imperative to develop an AI screening method to facilitate medical workers, thereby to reduce their workload and to help with the more precise diagnosis. So the aim of the ICEP 2021 COVID Challenge is to develop a fully automatic framework that is capable of recognizing CT scans and thereby categorizing them into three classes, including patients infected with COVID-19, CAP, which means common pneumonia, and also normal patients. Now, let's take a look at the data set. In this slide, I listed several important features of the data. As mentioned earlier, it has three classes. All of the CT scans are saved in DICOM format. For each patient, the volume is 3D, and it should be noted that there are two critical parameters as pixel spacing and slice thickness, which will be used for the subsequent process. Next, let's turn to our contribution and originality. So generally speaking, our method includes two critical sections, a novel data pre-processing pipeline and the pre-trained 3D ResNet. Now let's talk about the dataset pre-processing first. As mentioned earlier, the dataset is in DICOM format. So the first step is to extract the pixel data of the CT volumes. Then the second step is to resample these CT volumes. For the resampling, we're going to use the two parameters I mentioned earlier as pixel spacing and slice thickness multiplied by a experimentally acquired coefficient. It should be noted that this step aims to generate more slices, thereby to augment the spatial information of the data. As illustrated in this figure, you can see that the volume became more volumetric and more solid after the resampling process. The next step is the pulmonary segmentation or lung region segmentation. This is a vital step in the whole pre-processing procedures, basically because pneumonia is a type of severe respiratory syndrome. So the region of interest is only the lung area. This slide demonstrates how the segmentation works. It is noted that the threshold value for the binary image, the third one, is experimentally acquired, so we can have a clear mask image for the lung region. And the final step is once we have a clear mask image, we multiply it with the original image, so we obtain the final segmented lung slice. And this slide illustrated this step in 2D perspective. And now let me show you a 3D perspective segmentation so you can have a better understanding of what this step really does to the volume. As you can see that after the segmentation of the 3D volume, it has a clear spatial shape of the patient lung. The next step is also very important, which is the slice range selection. So the reason why this step is essential is that if we first look at the annotated data of the original data set, the slices that are labeled with infections are mainly distributed in the central area of the volume. So the problem now is how we are able to extract these slices with infections so we can improve the accuracy of the COVID detection. And here we employed a slice range selection approach to extract slices that are more likely to have salient features. The basic idea is once we have the clear mask image, we first calculate a column of the area that the long region account for the whole slice image. Then we normalize the column by dividing the maximum area value. So we obtained a column of normalized long region area. Then we only took those slices that with the area value that more than 70%. And after the extraction of slices with salient features, we need to resize the volume into 224 cubic because it is the required input size for the 3D ResNet. So, and then the volume is ready for the input. Moreover, we also used a data augmentation method. This data augmentation method only aims to balance the dataset because we have way more patients of COVID than CAP and normal. So only the CAP and normal patients data are augmented by setting different resampling parameters and also applied a random center image crop. And this table shows the details of the dataset for training. Let's go through the training step. The backbone network for this project is the pre-trained 3D ResNet 50. And it is worth mentioning that we did not change the architecture of the network due to the complexity, and we applied a straightforward transfer learning with a 3-class classification layer for this task. This slide illustrated the training options, and the whole training process is implemented using MATLAB. And this slide exhibits the experimental results for the model evaluation that it achieved an overall accuracy of 87%. So why we're using four-fold cross-validation is because that the organizer of the challenge didn't provide the label of the testing data. Thus, in the experimental stage, we have to split 20% of the original dataset to evaluate the model performance. And the second table is the final testing results for the competition. And our team ranked number 4 for the final trial with an overall accuracy of 85%. Since the organizer did not release label information, so we are not able to calculate, the whole metrics. To summarize, our approach yields a quite good classification accuracy in the IEEE COVID competition. And it is a promising approach for practical use because the framework is fully automatic and the implementation will be very simple and straightforward. So that brings us to the end of this presentation. And that's all. And thanks for watching.